Going on, guys. Today I'll be talking about initial and final value theorem. Okay, since this will be helpful in time domain response, that's why I'm covering it separately for the time response part. Okay, so first I'll cover initial value theorem in this page, as you can see, and in the second page, second side, I'll cover final value theorem. Okay, so first I'll talk about initial value theorem. As you can see, initial value theorem can also be called as IVT. Here I have given the definition. Okay, C of 0 is equal to limit t tends to 0 Ct, or it can be equal to limit s tends to infinity s into Cs, where C0 plus will be the response at t equal to 0. Okay, C is the sum function of t. Okay, for example, you can see t square plus t plus 1, or Ct is equal to e to the power minus at, where Cs is Laplace transform of Ct. Okay, so there will be one signal which will be time domain, which will be in time domain, and you can see initial value theorem in time domain will be this: limit t tends to 0 C of t. That's it. Okay, you can also solve it by using Laplace domain. This will be the initial value theorem for Laplace domain. Limit s tends to infinity s into C of s. Okay, where Cs is the Laplace transform of Ct. Here you just note that this limit is from t tends to 0, and this limit is from s tends to infinity. Okay, so this will be the initial value theorem. I'll give you an example. You can see Ct is, I have taken Ct is equal to e to the power minus 2at plus e to the power at ut. Ut means for ut is a step signal. Okay, so you know that step signal will be 1 for t greater than equal to 0, ut will be 0 for t less than 0. Okay, so this is just to say that the response will be means the response will be there after t greater than equal to 0. Okay, just why this ut is multiplied with this function. Okay, so this is my function. I'll apply in time domain first and then in frequency domain. Okay, in time domain you can see I've used this formula: limit t tends to 0 Ct, limit t tends to 0 Ct is equal to limit t tends to 0. I've put this function here. Then I separated limit, as you can separate. I mean, limit a plus b can be written as limit a plus limit b. Okay, like this, and then you apply t equal to 0 here. So e to the power minus 0 will be 1, e to the power 0 will be 1, so the total answer will be 1 plus 1 is equal to 2. Okay, now we'll apply this in frequency domain, that is Laplace domain. Limit s tends to infinity as Cs. Here Cs is Laplace transform of this function. You can see Laplace transform 1 upon s plus 2a 1 upon s plus a. Okay, I'll put IVT is equal to limit s tends to infinity s into this function. Okay, now you'll apply. Since you have in limit s tends to infinity, always try to take out s as common, so that s will come in denominator. That's how usually you solve. Okay, that's how you will be able to apply the limit. You can't apply directly infinity. If you apply directly infinity, that will be infinity upon infinity, that is undefined. You can't do that. Okay, so here I have multiplied s inside and I separated the limits, so you will get limit s tends to infinity s upon s plus 2a s upon s plus a. Now I have taken s out from the denominator, so you can write it as s1 plus 2a divided by s as 1 plus a divided by s. This s will be cancelled. You can see s is in denominator. Now if I will apply limit s tends to infinity, it will be 0, because 1 upon infinity is 0. I'll write 1 upon infinity is equal to 0. Here if you put the limit, this will be 0, this will be 0, so overall 1 upon 1 plus 0, 1 upon 1 plus 0, that will come as 2. You can see these two answers are matching. Okay, so this is the initial value theorem, but you have to make sure there is a condition. you have to make sure that condition is satisfying or not. In frequency domain, you have to note that it is applied only when the number of poles of a function of CS is more than the number of zeros. That is, the function should be strictly proper, means there should be more number of poles than the zeros in a CS transform. CS right now, just take it as CS. So here I have given an example. You can see this is the signal. Okay, so I have applied initial value theorem in time domain. You can see del t at t equal to 0 will be 1 minus e to the power 0, that is 1, and ut will be 1. Okay, so 1 minus 1 will be 0. Okay, but in frequency domain, if I'll apply this Laplace transform is 1, del t's Laplace transform is 1, for this Laplace transform is 1 upon s plus 2. When you take LCM, this will come as s plus 1 divided by s plus 2. When you will apply this in frequency domain, you can see s tends to infinity, s into this. Since here the number of poles is equal to number of zeros, one pole is there and one zero is there, the condition is the poles should be greater than zeros. Okay, the number of poles should be greater than zeros. Okay, so when you will apply here, I'll take s common from both the sides, so I'll get 1 by s, 2 by s, 1 plus, so that I can apply limit, but because of this s, it will come as infinity. And you can see this is not the same as what we got in delta t time domain formula. So the point I want to give you is you have to make sure that when you are using frequency domain, then you should satisfy this condition, and if it is not satisfied, you should go back to time domain response and you should satisfy that. You should take out the value, then calculate the value from time domain approach. Okay, and usually we go by this method, frequency domain method, because it is easier to calculate and you don't have to calculate the inverse Laplace transform, so that you can apply this time domain formula of initial value theorem. So everything works out, but you have to make sure this condition satisfies, then only it will work, else you have to take the Laplace inverse and you have to apply the time domain approach. Okay, so this thing you should take care in mind. Okay, now I will go to final value theorem. So final value theorem states that this is limit t tends to infinity ct is equal to c infinity, means the value we are calculating is final, means at last what will be the value when you go on time, when you will increase the time, what will be the value of c at last, means when the time is very very high. Okay, so this limit t tends to infinity ct is equal to c infinity. You can write it as c infinity. That is also can be written as s tends to 0 s into cs. Here this is frequency domain approach, this is time domain approach. It is similar to initial value theorem, but you should take care of limits. Here in time domain t tends to 0, but in frequency domain s tends to infinity. And here if you will see, in time domain t tends to infinity and s tends to 0 in frequency domain. So this is the final value theorem. Okay, but here also it's like one condition is there, and that is not the same as this one. So the condition is this final value theorem will only be applicable when the poles of s into cs will be on the left half of s plane, not even on j omega axis. Means take care of this thing guys, s into cs poles should be on left half of s planes, s into cs, not for only for cs, s into cs. For s into cs, the poles should be on left half of s plane, not even in j omega axis, not even in right half of s plane. All the poles should be in left half of s plane, then only you can apply this final value theorem in frequency domain. Else again you have to shift back to time domain through inverse Laplace transform, and then you can apply the time domain approach to calculate the value. Okay, so I'll give you an example. Here I have covered both initial and final value. This example is related to time domain response, which I'll be showing you in, which will be useful in time domain analysis of time response analysis of control system. So here you can see I have taken a transfer function cs divided by rs, that is 10 into s plus 4, 10 divided by s plus 2, s plus 5. This is output and this is input, rs is input. You have to compute initial and final value of a response for unit step input. Input is rs and response will be cs. Okay, so cs can be given as 10 upon s into s plus 4 s plus divided by s plus 2, s plus 5. Since rs is given as 1 by s, Laplace transform of step signal. Okay, you can see. Now I'll apply IVT in frequency domain since it is easier. So you can see s tends to infinity, s into cs I have written this. Okay, initial value theorem, I have to make sure that poles should be greater than, number of poles should be greater than number of zeros. So here the number of poles is greater than number of poles is greater than number of zeros. Okay, so when you apply here, you can see I'll take, since s tends to infinity, I have to take common something, s common I have taken here, s common here, s common here. Here s square will come, here s will come, because only s I have taken common. From here 1s from here and from 1s from here, that's why s square. SS will be cancelled, but 1s will be remaining, that's why if you apply infinity, it will come as 0. Okay, now I'll go for final value theorem. Limit s tends to 0, scs is equal to ss cancel 10 s plus 4 divided by s plus 2, s plus 5. And you apply the limit, you have to make sure c into ss, cs, s into cs, sorry, s into cs, s into cs will be my this, and you can see there is no pole on the j omega axis on or on the right half of s plane. All the poles are on the left half of s plane, even the zeros are also in the left half. So you can see this will be -4, this 0 will be on -4, this will be in -2, this will be in -5. So all the poles are in left half, even the 0 is in left half. Okay, so you can apply this final value theorem. So s tends to 0, when you will apply, you will get 10 into 4 divided by 2 into 5, that is 4. Okay, so this is the initial value. It means it will start the response for step input. The response for a step input, it will start from 0 and it will go till 4. You can see this is the meaning of initial value and final value theorem. It will start from 0, it will go till 4 finally. Okay, you can write c0 is equal to 0, c infinity is equal to 4. If we by chance some of the conditions were not satisfied, then you have to switch it back to the time domain from Laplace domain. You have to take inverse Laplace transform, and then you will have to apply the time domain approach. Then you have to check whether you are getting a value or not. Okay, so you can see note final value to a step unit step input is equal to, yeah, one more thing, yeah, this point you have to, means like an extra, it's like an extra point. Whenever there is a final value to a step input, final value if you will calculate, that will be equal to the DC or zero frequency gain, also called as steady state gain, that I'll be talking in time response also, but still I'll mention here. This is a zero frequency gain. See, this is a transfer function. If I'll put s is equal to 0, equal to DC response frequency gain. Yeah. When I'll put 1 minute guys, yeah, sorry, this is the transfer function for the step input. This will be the zero frequency gain, 0 0 0. So 10 into 4 divided by 2 into 5, 10 into 4 divided by 2 into 5, that is, so this will be the zero frequency gain, you can call it as. This is some extra point I wanted to make sure that you guys know about this thing. That is not so important in final value or in initial value theorem. Okay, so that's all guys. If you feel like I've done some mistake or I should include something, then let me know in the comment section. Okay, and I'll see you guys next time. Thanks for watching.